Hello, I'm Michael Tonks. I'm a professor from the University of Florida. And today I'll be talking about the work that we've done on the performance of UO2 reactor fuel with high thermal conductivity additives. And this is work that I did, that really my student Floyd Hilty did. And he's now graduated and is a postdoc at Pacific Northwest National Lab. And this work was actually funded from an IRP led by MIT, and it was entitled The Development of Accident-Tolerant Fuel Options for Near-Term Applications. Now, as many of you probably know, a nuclear reactor is essentially just like any other power plant, like a coal plant or a gas plant, where heat is converted into electricity, but instead of that heat being generated by burning fossil fuels, it's generated by the fission of uranium atoms. And so we have our fuel material where the fissioning is taking place. So now this heat has been generated inside of the solid fuel, and it has to be conducted out of the fuel, and in order for us to then take that heat and convert it to electricity. And so the thermal conductivity of the fuel directly impacts the efficiency and the safety of the nuclear reactor. Now, the vast majority of nuclear reactors in the world are fueled using uranium dioxide. And uranium dioxide has a lot of good things about it. And one of those things that isn't quite so good is the thermal conductivity. It's fairly low. When you compare against other materials, it's closer to materials like ice or sandstone than metals, like even lead or aluminum alloys. Now, UO2 has other good things about it. The main reason it's been selected is because of safety issues. So everything related to safety is quite good when you compare against other uranium-bearing materials. It has excellent corrosion resistance in water, which is the coolant. It has good compatibility with the zirconium cladding material. It has great thermal stability, so it's not changing phase or has drastic changes in shape or anisotropic thermal expansion or anything like that. And it has a very good melting temperature, very high. And so you can get to high temperatures. But the problem is related to efficiency. It has a low uranium density and this low thermal conductivity. So we want to be able to maintain all of these benefits of UO2, but also increase the efficiency. And an approach that a number of different researchers have attempted is to take uranium dioxide, but then mix in other materials to create essentially a composite fuel and trying to raise the overall thermal conductivity of the material. And people have tried to mix in lots of different materials, including diamond and graphene, beryllium oxide, silicon carbide, metals like molybdenum or tungsten, or even other fuel materials like uranium nitride or uranium silicide. So another way to look at this is it's sort of like cold stone. So in cold stone, you go in, you choose your ice cream, and then you can add in different mix-ins to make the ice cream more interesting. With these composite fuels, we have our base uranium dioxide fuel, and then we just choose our mix-in. What is the material that we want to go mix in to try to raise that thermal conductivity? And so we choose different volume fractions of this additive to add in to raise that thermal conductivity. Now, for all these materials that are colored in black here, these are non-fissile materials. And so for all the volume fraction that we add, we're actually lowering the uranium density. And so we're lowering the amount of heat being generated. So we don't want that volume fraction to be too large. The exception to that are these two that I've shown here in blue, uranium nitride and uranium silicide, where these are fuel materials. In fact, fuel that has a higher uranium density than UO2. And so they not only raise the thermal conductivity, they raise the fuel density as well. Now, there's a review article by Zhou and Zhou in 2018 where they looked at a bunch of these different fuel materials, and they compared their thermal conductivities. So the black line is a common fit used for the thermal conductivity of UO2. And then you can see how these different composite fuels, all with fairly small volume fractions of 5% or less, compare. And we can get benefits and various benefits to adding these additives to the fuel. Now, if you look at it even closer, another really important aspect pops up. So here are two microstructures from beryllium oxide. And where we've added beryllium oxide, and they have the same volume fraction. But in one case, that beryllium oxide has been, it's specifically located along grain boundaries. And then the other case is just dispersed throughout the material. So we have more of a continuous structure or a dispersed structure. And the comparison, and this is from Ishimoto, that they found experimentally is that you can have a very large benefit of this dispersed structure, or sorry, the continuous structure over the dispersed structure. So the microstructure has a large impact on the thermal conductivity of these composite fuels. So today I'm going to talk about two different projects that we've done looking at these composite fuels. First off, where we've developed a simple thermal resistor model where we have a model that can capture a range of different types of composite fuels and estimate the effective thermal conductivity, and it takes into account the microstructure of the fuel. And in the other case, we've looked at these composite fuels, but specifically looked at what is the impact of fission gas on their improved thermal conductivity. So first, I'm going to talk about our simple thermal resistor model. And so the idea behind this model is we want to be able to represent the effective thermal conductivity of various microstructures with the same basic model. And so the idea is we've taken this range of different structures that we could have in the fuel, and we've boiled them down to sort of their most basic elements. So we have the fuel, and we have some additive that's essentially in parallel to the fuel, where the heat can transport along this continuous phase without touching the uranium dioxide. And then we have some additive that's essentially in series with the UO2, like these dispersed particles. And then we also might have either interfacial resistance or voids along the interfaces, and we need to account for their contribution as well. And so then depending on the amount of additive, either in parallel or series, we can transition between different types of microstructures. And so we end up with 4 thermal resistors. And we can take those 4 thermal resistors and get the effective resistance, and then turn that into the effective thermal conductivity, and make it all a function of the thermal conductivities of the individual phases, the UO2, the additive, and the voids, and also the volume fraction of this secondary additive phase and the void phase. But then we also have a parameter P, which is the continuousness. What fraction of the additive is along this parallel path? Now, in order to determine a way of estimating that continuousness, we've tried to build in the basic ideas of heat transport, where the heat wants to flow essentially through the path of least resistance, as we try to, the flux is in the direction of the gradient of the concentration, and it moves through the material. So we draw a path through the material where we try to stay within the high thermal conductivity additive as much as possible. But we also try to make that path as straight as possible as well. And so we end up with this parameter P, which is a function of C, where C is the path length that's in the secondary phase divided by the total path length. So this sort of winding path. And then D penalizes paths that are not straight. And so we take the total path length and divide by the actual width in the direction of heat transport, which would be the shortest path that you could follow. And from that, we get this value for P. However, having to do this by hand, draw these lines and trying to stay within the other phases is a burden and is sort of a pain, but also it can lead to a lot of dependence on the user. And so we've also taken or developed a genetic algorithm where it takes a binary image where it's either black or white, where white is the UO2 and black is the high thermal conductivity additive. And it actually draws these paths, and it tries to minimize, to maximize the continuousness of each path using this genetic algorithm. And so you just provide the image of your microstructure, and then it estimates the additive, and it does it at multiple paths, and then takes an average of those values to get the average continuousness. So we've applied our model to various microstructures from the literature where they've measured the thermal conductivity of their microstructures. So we have UO2 with continuous beryllium oxide and with dispersed beryllium oxide. That's from the Ishimoto paper. And then there's actually two works that were done previously by Chelenko and his colleagues here at the University of Florida, where they have UO2 with whiskered silicon carbide or powdered silicon carbide. So we took these images and we applied the genetic algorithm and then used our effective thermal conductivity model. And you can see the error for different ratios of the UO2 thermal conductivity and the thermal conductivity of the additive. And what we find is that the errors are fairly low, 15% or less, but in general, but they tend to increase some with this thermal conductivity ratio. And we also find that there's this one sort of outlier microstructure where the silicon carbide, the powdered silicon carbide, this one, which was worse, but still, 35% error or less, but not nearly as good. Now, the next question is, well, does this approach even make sense? Well, we can take a micrograph, which is just a slice of a 3D microstructure, and just with that one 2D slice, estimate the overall thermoconductivity of the 3D microstructure. And so to check that, we actually constructed a way to generate 3D microstructures in the MOOS code. It's a finite element code. And then we have estimated the effective thermal conductivity of these microstructures with the finite element method. But we wanted microstructures that were similar to these from the actual experimental data. So we reproduced the microstructures from the experiments. And then we came up with ways of generating microstructures that had very similar characteristics. And we compared their characteristics and also the thermal conductivities and made sure that they compared well. And once we had this approach working in 2D, then we just ran it in 3D and we have our 3D microstructures. And what we did is we would take a 3D microstructure and calculate its effective thermal conductivity, and then randomly take multiple slices of that 3D microstructure and make images of it, and then use the thermal resistor model with the genetic algorithm to estimate the thermal conductivity of those different slices. And we compared them against the 3D simulation. And in general, there was some scatter between slices, but it was not large, and they overall compared well with the thermal conductivity from the 3D simulation. The one exception to that was the same powdered silicon carbide microstructure where the model itself didn't perform very well compared to the experiments. And we could actually get a good reason of why that is. And in this case, here's a microstructure where it performed very well. There's very little scatter between 3D slices, and it compared very closely to the 3D simulation. We have a lot of particles, and including big and small particles. Now, when we look at this microstructure which performed poorly, we do not have very many of these large particles. So there's not enough to get a good statistical description of these large particles. And because of that, we don't have a good statistical representation of this microstructure. So it's not a representative microstructure of the material, which leads to this large scatter in the different slices of our 3D microstructure. And it also resulted in our model being less accurate. So as long as we have a good representative microstructure, then our model works well to estimate the thermal conductivity. And we can now use this idea of continuousness to try to design and help optimize microstructures that result in the best benefit for a certain amount of additive. So we first looked at dispersed particles where they have different aspect ratios. And so the orientation now matters. And the orientation could be random, or it could be all oriented in the direction of heat flow. And so they're very lined up. And we looked at ellipsoids, and we also looked at rectangular particles. So if we look at ellipsoids, and we look at the continuousness, which is directly impacting the thermal conductivity, the first thing that we see is that random distribution of particle orientations gives us the lowest effective thermal conductivity. But then as we align them more and more, it starts to improve, but it eventually stops improving. We get to the point where even additional alignment does not significantly improve the thermal conductivity. And that happens at about plus or minus 30 degrees. And when we look at the rectangular particles, we see the same behavior, that as we go from random to 15 degrees, we get a large alignment within, 60 degrees, we get a large benefit. And then when we go up to 30 degrees, we get a benefit. But as we go up to 15, there's no additional benefit. So again, 30 degrees is about the best we get, even when it's compared to fully aligned microstructures. So it is very useful, and you can help maximize the thermal conductivity by aligning your additive in the direction of heat transport, but only up to a point, and then you don't have to have full alignment. The next thing we looked at is how can we improve the microstructures of these continuous structures, where we have the additive around the grain boundaries. And so again, we generated different microstructures and looked at their continuousness. And first off, as we increase the coverage of grain boundaries by our additive, so the additive grain boundary coverage, we get a very strong correlation. The more coverage we have, the higher the thermal conductivity, irrespective of other aspects like the volume fraction and so on. If we just look at the impact of the thickness, so compared to this very thick, thinner, and then quite thin, we don't see a huge impact of that. And so though the coverage matters, if you thin it out to try to minimize the overall volume fraction, you're not going to significantly decrease your thermal conductivity up to a point. There will eventually come a point where you're thinner than the photon mean free path or the electron mean free path if it's a metal, and then you're not going to get that same benefit. So we've shown then that these high thermal conductivity additives definitely have a benefit. They can raise the thermal conductivity without significantly lowering the amount of fuel, and we can get a benefit at lowering the centerline temperature. However, once we put them in a reactor, things start to change. Experiments have actually shown, even in shorter radiations, that certain materials like silicon carbide are not even stable. You heat it up and irradiate it, and the silicon carbide just disappears. But other materials like beryllium oxide have been shown to be stable even at elevated temperature and radiation. However, we're going to get fission products forming, and some of those fission products are fission gas. And we know that fission gas tends to segregate to grain boundaries, and we get these interconnected networks of bubbles along grain boundaries, and that's how we get fission gas release. So now if we throw in these particles, we're adding additional interfaces for fission gas to segregate to, and interfaces that are probably going to have more free volume than a grain boundary. So they might be even more preferred segregation sites than the grain boundaries themselves. And so we're going to start concentrating fission gas around these particles. And we can imagine that's going to significantly impact the thermal conductivity, and we might start to lose the benefit of these high thermal conductivity additives. So we wanted to explore that, and we're exploring it. We're exploring it using a fairly simple system. So we have a 2D system with a single additive particle. And then we used a fission gas model to predict the formation of a bubble on that grain boundary with a different contact angle, which is going to be due to the ratios of the interface energies of the interface between the particle and the UO2, and also the surface energy of the UO2 in the particle. And so we get a range of different contact angles, and we looked at all these different contact angles. We have some with highly wetted and some that were much larger contact angles, and so the bubble did not significantly wet. And we looked at different gas volume fractions. And we also looked at different positions. In these cases, the bubble is in the direction of heat transport, which is to the right. But then we looked at having bubbles on the top and bubbles on the bottom and maybe multiple bubbles. And we also looked at rectangular particles instead of spherical particles. And so we represented them, and we used mousse to calculate their effective thermal conductivity, where we assigned different thermal conductivity to the additive, the UO2, and to the gas. So here are the results. So specifically, this is for beryllium oxide and uranium dioxide at 300 Kelvin. And here I'm showing some lines for reference. We have a fresh composite fuel without fission gas is this orange line. We've got the green dashed line here is pure UO2, and then the pink line is UO2 without additive, but with a gas bubble of the same volume fraction. And then here we have the rectangular particles with the same lines. And the first thing that we see is that depending on the particle or on the bubble position and wetting angle and volume fraction, we get a very large scatter. When we have the bubbles rotated so they're up on the top of the particle and they're not blocking any of the heat transport through the particle, they have almost no effect in both the sphere and the rectangular particles. But then as we put them in the direction of heat transport, we get an increased effect as we increase the volume fraction, but the slope is directly impacted by the contact angle. So the more wetted they are around that the particle, the more it blocks heat transport, to the point where in the extreme cases where we have very small contact angles, so 35 degrees and 45 degrees, and especially let's look at the 35-degree case. As we get even just to 4% fission gas, we've completely eliminated any benefit of our particle. It's as if that fission gas bubble was just sitting in the UO2 without any additive at all. Now that's significant, right? So this is worst case, obviously. In other cases, it has very little effect, but worst case, we can have a very large effect. So we wanted to look at that even further. So we went to larger bubble volume fractions just for these 35-degree and 45-degree contact angles when the bubble's in the direction of heat transport, so sort of the worst cases. And it gets even worse. We get down to the point where we've eliminated any benefit of the bubble, but then it even gets worse than as if there had been no additive in the first place. And the reason for that is because we've changed the shape of the bubble. In the case where we're assuming there's no additive, we get a spherical bubble. And when we have additive, we get this crescent bubble where we've spread the gas out a lot more in the direct perpendicular to heat transport. And so it's blocking much more of the composite particle, the high thermal conductivity particle. And essentially it's approaching the line that I'm showing here. The blue line or the orange line are the thermal conductivity if we just had a bubble with no particle at all. And so they started approaching that, which of course is going to be worse than the spherical bubble. So when we start getting fission gas around our particles, this can be a very large effect. And this is of course aimed specifically at dispersed particles, but this can be a big issue. So we need to understand this and be able to predict this behavior. So the next step is to try to come up with some metric that describes the geometry of our fission gas bubbles that has a good correlation with its effect on the thermal conductivity. So we looked at a number of different metrics, and we look at the bubble volume fraction, which we already looked at. There's no clear distinction. There's a big spread. When we look at the surface coverage fraction, which is the overall fraction of the surface area that's covered by the bubble, we again don't see any clear correlation. Now, if we look at the cross-sectional coverage fraction, which is the fraction of the cross-sectional area of the high thermal conductivity particle that's blocked by the fission gas bubble, now we start to see these various dots start to collapse on top of each other. And then if we go to the screening fraction, where it's the fraction where the fraction of the total area across, or really the total volume of the particle that's been blocked by the fission gas bubble, then they line up on each other very nicely. And then we're only distinguished now by whether we have a spherical particle or a rectangular particle. So we're going to use the screening fraction, and we've developed a model. We can normalize the thermal conductivity by the fresh composite fuel. And now we get the thermal conductivity sort of collapse onto each other even more, but we still have a distinctive curve for the spherical particles and for the rectangular particles. So we've come up with this model, which is the normalized thermal conductivity as a function of the screening fraction squared. And then we have K1 over K naught, where K1 is the thermal conductivity of fresh composite fuel. Sorry, K naught is the thermal conductivity of fresh composite fuel, and K1 is the thermal conductivity of standard UO2 at the whatever burnup of interest that we have. So essentially the case where there's no, we have the same amount of irradiation and damage with no additive at all. So we're assuming that over the whole microstructure, we're going to sort of average out those worst case scenarios where it actually gets a little worse. And then we have to come up with some way of representing the change in the geometry. So that's what this A parameter is for. And we just fit it, but we don't fit it to the data. We want to be able to compare against the other simulation results that we've already shown you. We're just going to fit against very simple microstructures where we just do rectangles, and we're just changing the aspect ratio in the direction of heat transport of the additive. And we have the gas just being a rectangle. And we fit to that to get our fit for A. So we've calibrated this geometry coefficient that describes the geometry of the additive. So now let's look at how this model performs. So this figure over here on the left is showing the comparison for all of the results that I've shown you previously. So this is with UO2 and BEO at 300 Kelvin, and for both the spherical and rectangular particles. And we get very good predictions. The model predicts very closely to what we got from the finite element method. But we wanted to test this in other conditions. So the first thing that we did is we changed the temperature. So we still used UO2 and BEO, but we looked at 3 different temperatures: 300 Kelvin, which is of course the result here, 900 Kelvin and 1500 Kelvin. And these are just for the spherical particles. And the dashed line in all these cases is the pure UO2. So what we can see here is that, again, the model compares very well. And we get a great comparison. Now here we've kept UO2 at 300 Kelvin, but now we're changing the additive. So we have 3 different thermal conductivities of the additive that we're trying, and we're increasing that. And again, the model performs very well, but we get actually some interesting results here where we're showing that there comes a point where even if you increase the additive thermal conductivity even more, you don't get any additional benefit. We sort of hit a threshold where we can't get any better, even if you double the thermal conductivity of the additive. And then the last case, we have a bulk thermal conductivity that's changing, but we're always using the additive thermal conductivity of beryllium oxide at 300 Kelvin. And again, the model is performing well. So we've now demonstrated that the bubbles can have a large impact on the thermal conductivity of these additives. And we've also developed a model that can start to capture that effect. But these very simple simulations, and they are really only applicable to dispersed microstructures. So microstructures that are continuous, the bubble interactions are going to be different, and they're going to be more spread out across the grain boundaries. And I suspect that they're going to be less impacted by the bubbles, because even if we have a lot of bubbles on either side of this additive, we still have a continuous path for the heat transport to move through along those grain boundaries. And so I suspect, again, we still need to look into this, but that it's going to be more resistant to the impact of fission gas than these dispersed particles. So just to conclude, we've shown first that we can estimate the effective thermal conductivity of these composite fuels, and we can do it well, and we can account for the microstructure using a genetic algorithm to predict this continuousness. And then we used that idea to begin to get some idea of how we can optimize the impact of the additive by changing the geometry. We then looked at the impact of fission gas bubbles, and what we found is that in worst case, when we have dispersed particles, a fission gas bubble can completely eliminate any benefit of the additive and even make it a little worse because it's spreading the bubble out more and blocking more of the heat transport. And we've developed a a simple model of this effect, where it's a function of this screening fraction that seems to describe the behavior reasonably well. And with that, I'll end, and please enter your questions into the chat, and I'd be happy to answer them. Thanks.